section 16D. We're looking at inflections and shape. So when we're looking at a curve and we have a curve that is shaped this way, we call it concave down. When it's shaped this way, we call it concave up. So those are parabolas. In this instance, they're parabolas, but they could be just a certain part of a graph, for example, like this. Okay, so this would be concave down, this part would be concave up, this part would be concave down. If we take a look at the shape of that and we think about the slope of the tangents to each point on that concave down line. So here we have concave down. Take a look at all of these slopes across here, slopes of tangent lines. That slope is bigger than this slope, which is bigger than this slope, which is bigger than this slope, which is bigger than this slope. So as we are moving to the right across our graph, the slope of the tangent lines are decreasing. Okay, the slope of the tangent lines decreases. Okay, the slope of the tangent lines is the derivative function, so we're saying that the derivative is decreasing. If we look then and think about from the last section, 16C, when we drew a sign diagram of a derivative function, and we had some point here, say x equals a, if we had negative here, positive here, it meant from our original function that on this interval of the graph, the original function is decreasing. This interval of the graph, the original function is increasing. This sign diagram also means that on our derivative function, in this portion of the graph where it's negative, the graph occurs below the x-axis. In this portion of the graph where it's positive, the graph occurs above the x-axis. Similarly, if we're looking and comparing the derivative to then the second derivative, so we're talking here its derivative, we're talking about the derivative of the derivative, we're talking about the second derivative. If we draw a sign diagram of the second derivative, parts of the second derivative, if it was positive and negative, say, about a certain point A, this would tell us what the second derivative function looks like with regards to this positive sign, meaning that for the second derivative, the graph occurs above the x-axis. For the negative sign, the graph occurs below the x-axis. But it also, like up here, we could compare it to the next derivative down in that it tells us that the first derivative in this portion of the graph is increasing and in this portion of the graph is decreasing. Okay, so just like back in section 16C, looking at sign diagrams, we could make a connection between a derivative and an original function. Looking at sign diagrams now, we will be able to make a connection between a derivative and a second derivative. So back to this example, the gradient of the tangent line decreases, therefore the gradient function, derivative function, is decreasing. The derivative of the derivative, the second derivative, is negative. Okay, this is the way we can write that. Second derivative is negative. It's less than 0, means the same thing as it's negative. If we're looking at a concave upwards graph and we compare the slopes of the tangents as we move to the right along the graph, these slopes are getting larger. -1 is larger than -2. 0 is larger than -1. 1 is larger than 0, and so on. So as we look at this curve, the gradient of the tangents are increasing, therefore the derivative function is increasing. The derivative of the derivative will then be positive because increasing of one function refers to positive of the next derivative up. Okay, so therefore the second derivative is greater than 0 or is positive in this case. just reaffirming what we've already talked about. The second derivative is the derivative of the first derivative. So recall. When we talk about the first derivative, it can tell us something about the original function. It can tell us important facts about f of x. For example, if the derivative is larger than 0, in other words, it's positive, then we know that the function is increasing. If the derivative is less than 0, so negative, we know that the derivative is decreasing. And if the derivative is equal to 0, we know that we have one of those stationary points. And remember, there's 3 situations: a local minimum, a local maximum, and a stationary point of inflection, or horizontal point of inflection. Similarly, the second derivative can tell us important facts about the first derivative. If the second derivative is greater than 0, so again we're talking it's positive, then the first derivative is increasing. Now remember, this means that the gradient of the tangent lines is increasing. It's increasing. There's only one situation where this can happen. The tangent lines are increasing, and that is in this situation where we have a graph that is concave up. Okay, now I should have set up here, this second derivative tells us important facts about the derivative and the original function f of x. Okay, so it tells us that the derivative is increasing, and it tells us that the original function is concave up. If the derivative is less than 0, so it's negative, then the first derivative is decreasing, which means that the gradient of the tangent lines are decreasing. Therefore, f of x is concave down. And we're talking about this situation here, where the gradients are decreasing as we move to the right. And of course, there's a third situation here, if the second derivative is equal to 0. This indicates a point of inflection. Point of inflection on f of x. This could mean concave up. It could mean concave down. It could mean changing from concave up to concave down, or it could mean changing from concave down to concave up. So inflection points occur when the second derivative equals 0. So you would find the first derivative, find the second derivative, set that equal to 0, and see what x values make that happen. There's two situations. A stationary inflection point. This means horizontal. And a non-stationary inflection point. So not horizontal. We actually already talked about this situation in section 16C. It occurred when the first derivative was equal to 0, but, and remember there's three situations where this can occur: local minimum, local maximum, or stationary inflection point. Okay, so we've already talked about this. Stationary inflection point. That happened when, if we had this value, we had, and we took drew a sign diagram of the derivative, there was no change in sign around that critical value. Okay, so which meant that in this case the graph is increasing, the f of x is increasing, and it continues to increase past a. So it's increasing and continues to increase. Okay, but it has a stationary inflection point, which means that the tangent line here is horizontal. Or in the second case, it's decreasing and it continues to decrease. But we have an inflection point here and the tangent is horizontal. Okay, well now we have another way of looking at it. We're looking at the second derivative. So stationary inflection point, it's important to remember, has a tangent line with a slope of 0. Here's an example. If we drew a sign diagram of our derivative function and it looked like this, decreasing and decreasing, that means our original function is decreasing and decreasing. The second derivative has a sign diagram that looks like this, which means that the original function is concave up concave down, then that function would actually, original function would look like this. About A, the point A, it needs to be decreasing and concave up. Decreasing, concave up. So that's this portion of my graph. So decreasing but concave up. And this part is still decreasing but concave down. So decreasing, concave down. And then here is the tangent line. In the second situation, non-stationary inflection point, we would have a situation where it looks something like this. We've got a local max, a local min that we'll call B and C. We still have an inflection point here, but this inflection point does not have a tangent line that's horizontal. This inflection point has a tangent line something like this. So this is our original function. This is the tangent. And the slope is not 0. We would have a derivative function sign diagram that look like this. Here's our critical values for increasing, decreasing, increasing. So increasing, decreasing, increasing. And a second derivative sign diagram, negative, positive for concave down, concave up. And here it is, concave down, concave up. Okay, so there is a point of inflection if the second derivative at some point equals 0. And the second derivative changes sign at A. Now remember, inflection means that the curve changes shape. So in the vicinity of A, the second derivative sign diagram is changing. So in the vicinity of A, the sign diagram near A will either be plus minus or minus plus. This is a really good summary that the textbook shows on page 402, 403. So to date, in section 16C, we talked about this stationary point when the first derivative is equal to 0. And these are the 4 situations that can occur. We can have, these are all turning points. We can have a local max, maximum, a local minimum, or stationary inflection points, both of these situations. Now, 16D, we're looking at when the second derivative is equal to 0. So when the second derivative is equal to 0, there are points of inflection. Now these are broken down into 2 situations: stationary points of inflection and non-stationary points of inflection. If we tested the second derivative of a function and it equals 0, it will tell us that we have inflection points. Then, if we test the first derivative and it equals 0, then we know that those inflection points are stationary. If it does not equal 0, we know that They are non-stationary. Here's another way of stating what I just said up above. If the curve is concave down on an interval, then the second derivative is negative. If the curve is concave up, then the second derivative is positive. But this is what I said up above. If the second derivative changes at a certain value, we'll call it a, and that second derivative equals 0, then we have inflection points. We can categorize those inflection points into stationary and non-stationary then by testing the first derivative at that point. If it equals 0, it's a stationary inflection. If it does not equal 0, it's a non-stationary inflection.